Okay, Walter Rudin's Principles of Analysis, Chapter 1, Problem number 2. Prove that there is no rational number whose square is 12. So first we'll assume the opposite, that there is a rational number whose square is 12. So A over B, square of this number is 12. So the first thing I want to do is just reduce the problem down to what it really is. So what we're really asking is, okay, so this is going to be 2 root 3. Really, we want to know that there is no rational number whose square is 3. And I'll show you why. So A over 2b equals root 3. We just divided both sides by 2. This is really what we want to find. So first thing is we're going to call this something else. We're going to call it b over d. I'm going to prove that the square of some number cannot equal 3. So first we're going to assume this to be true, and we're going to assume that b over d is to lowest terms, or mutually prime. So we're going to get b squared over d squared equals 3, or b squared equals 3d squared. So that's just simple algebra. But here's where the part is. So if b squared literally equals 3d squared, and that's what it says, then 3 must be a factor of b squared. And if it's a factor of b squared, 3 must also be a factor of b. So I'm going to rename b. I'm going to call it 3k. Since 3, right, 3d squared equals b squared, so 3 is a factor of b squared. So then it's also a factor of b. So we're going to rename b. b equals 3k. So 3k squared, just for its replacement, equals 3d squared. And remember, this is the lowest terms. That's the assumption. So then we get 9k squared equals 3d squared. Simplify. K squared, 3k squared equals d squared. So we know that b equals 3k, or 3 is a factor of b. Here, d squared is 3k squared. We know that 3 is a factor of d squared. And if it's a factor of d squared, then 3 is also a factor of d. So b, 3 is a factor of b, and d is a factor, 3 is a factor of d. Contradiction to our original assumption of this number being to lowest terms, or mutually prime.